Hey, welcome to this video where we look at proof by induction, which is another one of our proof techniques. So what is proof by induction? Essentially, proof by induction is a specific methodology, approach that is useful for proving things that are in the discrete setting. So frequently propositions are cases that are governed by natural numbers. If the natural number is blah, then that means blah, some rule about that number. Proof by induction is a special tool that is used in this context. Let me just fill in some of that photocopying issue. And it also works generally for integer numbers. So let's just take a jump into the intuition of this proof technique, the logistics for how to use it, and then an example. Okay, so intuitively, what's going on here? We're dealing in the discrete world, and we're trying to prove a specific rule about usually natural numbers, but it could be any discrete context. And for intuition, I've just drawn this horizontal ladder here that is starting at the number 0 and then building up 1, 2, 3, 4 all the way through to infinity. And the idea of proof by induction is if you have some rule that says any natural number specifically does blah, 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 we can prove that rule by, first of all, showing that it works in the base case for the start of this ladder here, and then proving the transition between any step k to step k plus 1. And we do this in what we call the arbitrary sense, where we prove that k being any of these numbers will imply that k plus 1 works in terms of the rule. So if we can trust that k works in our premise, we're proving that that will imply k plus 1 also works. And then we essentially use this proof of k going to k plus 1 with our base case of 0 to then just start here and then go on forever. So we're proving the transition, we're proving the start, and together we're showing that we can access anywhere on the ladder in terms of the intuition. And that is this I suppose, high-level narrative of what proof by induction is. If we go down to the logistics, the way that we want to actually mechanically work things out is by doing the following. Let's say our rule is p of n, which is equal to just something about natural numbers n. We lay out our proof like this. Step 1, we verify that the first case holds. So above, that was the case of 0, but maybe it's the case of 1 or whatever it is in your specific context. Second step, we assume that p of k holds, and we don't need to prove p of k, we're just assuming p of k holds. And then in step 3, we prove that p of k plus 1 follows p of k. So this is the hard part. We're proving that this follows this. We're proving the inductive step of k leading to k plus 1. And if we've done step 1, 2, and 3, we've actually done the proof, and then we bring it all together with our conclusion, which basically says, as p of 1 is true and p of k plus 1 follows p of k, therefore we've proven our rule by mathematical induction. And that's it. So let's take a look at an example of this. So let's start here. We want to prove that the sum from 0 to n of 2i plus 3 multiplied by 3i is equal to n plus 1 multiplied by 3 to the power of n plus 1. And this is true for all n greater or equal to 0, all integers as well, by the way. And yeah, our goal is to prove that this is equal to this. And we're going to do that by mathematical induction. So let's actually write this one out together. So that is correct. Step 1 is verify. Yeah, maybe I'll flick it across. Just to quickly write out the sum. 2i plus 3 multiplied by 3 to the power of I is equal to n plus 1 multiplied by 3n plus 1 to the power of n plus 1. Okay, so step 1, verify the base case, which would be p of 0. And in this case, it makes sense to just write n is equal to 0. Okay, so left-hand side is equal to 0. Essentially, we plug in only 0 as I, and that's it. So that's 0 plus 3 to the power 0, which is 3 times 1, which is 3. And then the right-hand side is equal to 0 plus 1 multiplied by 3 to the 0 plus 1. That's 1 times 3, which is equal to 3. So left-hand side is equal to the right-hand side, therefore the base case holds. I'm just going to write that. Okay, then step 2. Assume n equals k. And I'll just write holds. So assume that we're just going to replace the n with a k. It's not the same thing with n because n is for any, n is a rule for all of these numbers, where here we're actually assuming k is just an arbitrary number here. So k plus 1, 3, and then k is an element of so k is just an arbitrary one of these, and we're assuming that it holds for that k. Okay, step 3. Consider n is equal to k plus 1. So the left-hand side is equal to k plus 1 in the sum there. And then the right-hand side is k plus 1 plus 1, so that's k plus 2. And then k plus 1 plus 1, k plus 2. We want to show the left-hand side is equal to the right-hand side. Okay, so let's start with our left-hand side. Now, the thing about an induction proof is we have from our assumption this, and we want to incorporate that into this next step here. So if we know that this here is equal to that, we want to leverage that, which means we want to convert this sum into an expression that has this in it. And in terms of sums, that's actually really easy because we just break down the sum by tacking on k plus 1 at the end. So if I plug in k plus 1 here and then sum to k here, that is the same sum overall. We get this. And then plugging in our assumption, we have these matching up. So we get k plus 1 and doing some tidying up. 2k plus 5. 3k plus 1. Yep, I think the algebra there is fine. And then we can factor out the 3k plus 1. And we have k plus 1 plus 2k plus 5. 3k plus 1, which is 3k plus 6. 3 to the power of k plus 1. And then perfect, we can factor out the 3 and we get k plus 2 and then plug the 3 into this to give us k plus 2. So that is equal to k plus 2, 3k plus 2, which is the right hand side. So factoring out the 3 here and putting it into this index is fine. Okay, so I'll just scroll to the pretty version here. Going down, we get left-hand side equal to the right-hand side, and thus we prove that k plus 1 follows k. And we can conclude our whole proof by induction using that statement. As n is equal to 0 holds and n equal to k plus 1 follows n equal to k, we have proven that the sum here, this rule, is equal to n plus 1, 3 to the n plus 1. And we've done that by mathematical induction. That's it. So that's our example. Just remember, when you're looking at using proof by induction, it's for discrete cases where you can use this intuition of proving k going to k plus 1 and verifying the base case. And you can do that in certainly microeconomic contexts in several creative ways where you're in the context of some discrete thing. But yeah, that's it for this video. I hope you learned a lot about induction. Thank you.